All right, we're continuing with chapter 4. We're talking about observational studies and experiments, which is one of the most important things in statistics, and understanding the difference between those two things. So an observational study observes individuals and measures the variables of interest, but does not attempt to influence the response. So an observational study is a hands-off approach. Okay, you are not impacting the subjects at all in any way. So for example, maybe I want to do a study and I want to see how the number of pillows you sleep with affects how many hours you sleep. If I just go and I ask you, how many pillows do you sleep with? And then I record the number of hours that you've slept. That's an observational study. I've not attempted to influence you at all. Okay, I'm not telling you how many pillows to sleep with. I'm just asking you, how many pillows do you sleep with? How long did you sleep at night? All right, that's an observational study. An experiment, and this is the key difference, deliberately imposes some treatment on the individuals. This is a hands-on approach. Now I'm telling you, okay, you go sleep with 2 pillows. You go sleep with 3 pillows. You don't sleep with any pillows. Now I'm telling you, I'm deliberately imposing a treatment. That's an experiment. When our goal is to understand a cause and effect relationship, okay, experiments are the only way that we can show a cause and effect relationship, all right? We cannot show a cause and effect relationship through an observational study. The distinction between experiments and observational studies is one of the most important things in statistics. So in contrast to observational studies, experiments don't just observe individuals or ask them questions. They actively impose a treatment. And that's the key difference between these two things. In an observational study, we're just observing. In an experiment, we are actively imposing some treatment in order to measure the response. All right, that's the difference between those two things. Observational study, hands-off approach. Okay, we're not imposing a treatment. Experiment, hands-on. We're saying you do this, you do that, and so on and so forth. We'll look at the example that follows in class. So in observational studies, the effect of an explanatory variable on a response often fail because of what's called confounding between the explanatory and one or more of the other variables. It's important when you're always talking about confounding, you always link the confounding variable to both the response and the explanatory. So confounding refers to the idea as I can't determine if the response that I got was because of my explanatory variable or some other variable. So for example, let's go back to our pillows and our sleep. I think the number of pillows affects the way or the number of hours that you sleep. In an observational study, I would just record how many pillows are on your bed, how long did you sleep. However, there are other factors that might affect the number of hours that you sleep. For example, what did you do that day? Your caffeine intake, your overall health. One other variable that might impact that is the size of the bed. Well, the size of the bed might have an impact on how long you sleep. Okay, so size of bed could be a potential confounding variable. When I discuss that confounding variable, I have to link that to both the explanatory and the response. So in this case, my explanatory variable, number of pillows, the response, what I'm measuring at the end, hours slept. When I describe that confounding variable, I want to say something like, the size of bed may be a confounding variable because the number of pillows, or people with a larger size bed, may also have a higher number of pillows on their bed. Therefore, I cannot determine if the reason they're sleeping longer is because they have more pillows or because they have a larger bed. So now I've linked that confounding variable to both my explanatory and my response variable, and I'm explaining why I can't determine if the response was because of the size of the bed or my actual explanatory variable, which is the number of pillows. Well-designed experiments take steps to prevent confounding. So in an experiment, we can alleviate this issue by saying everyone's sleeping on the same size bed, the same type bed, and so on and so forth. In an observational study, it's a hands-off approach. I can't control those other factors. So just to formally define confounding occurs when two variables are associated in such way such that their effects on the response cannot be distinguished from each other. So to formally define your explanatory and your response variables, your explanatory variable is what explains and causes the reaction or the result. This is what you had previously heard as your independent variable. Your response variable is the thing that you're measuring at the end, okay? It describes and measures the results. This is what you previously referred to as your dependent variable. We'll look at the next example here in class that's dealing with pulse rate and designing an experiment with pulse rate. Continuing on with some more vocab. So a specific condition applied to individuals in a treatment is, in an experiment is called the treatment. The experimental units are the smallest collection of individuals to which treatments are applied. When the experimental units are humans, we call them subjects. So all of you who are in my experiment with my pillows, you would be my subjects. The treatments would be the specific conditions, the number of pillows that you're sleeping with. A factor, variable. A factor, is a variable whose levels are controlled by the experimenter. The levels are the specific values that the experimenter chooses for a factor. And the experimental variable and the response variable, like we talked about, are your independent and your dependent variables. We'll go through the next part in class as well. One additional thing that you'll see in experiments is to make sure that your experiment is blinded or could be blinded. So in the experiment here that's dealing with caffeine and pulse rate, okay, it's important that both groups are blinded, so that the expectations are the same for the subjects in both groups. Otherwise, members of the caffeine group might suffer from the placebo effect. If the people measuring the response are also blind, then the experiment is considered double-blinded. So blinded refers to when the subjects don't know which treatment they're receiving. Double-blind means that the subjects and those interacting with them don't know. So again, blind means the subjects don't know which treatment they're receiving. Double-blind, both the subjects and those interacting with them now, obviously, if I'm the lead person running the experiment, I'll know which thing. But if I send my associates in to actually interact, then they don't know which person is receiving which treatment. So say I have 2 pills and I just say, okay, give this pill to this person and this pill to that person. Double blind, those people interacting with them don't know what they're giving to the people as well. Some more examples that we'll do in class follow. But let's talk about the principles of experimental design. These are the key things that you want to include, very important when you're designing an experiment. The first thing is comparison. You want 2 or more treatments or 2 or more groups. Second thing is random assignment. So you have to use some type of random technique to assign the experimental units to the treatments. Okay, doing so, and this is the important part, creates roughly equivalent groups by balancing some of the effects of other variables that might affect your response. So by randomly assigning, we're creating balance between our groups. Third thing is control. Keep other variables that might affect the response the same for all groups. So if we go back to our pillows and our sleep, maybe temperature might affect your response. So everybody is sleeping in a temperature of the same in their room. Maybe the bed type might affect your response. So everyone's sleeping on a certain mattress. Okay, all of those things are things that I can control. Replication is the next thing. You have to use enough experimental units in each group. So we can't just do it with 2 people in each group. I have to ensure that there's enough people in each of my groups. So if we take a look at this kind of diagram, this kind of shows exactly how you would design an experiment. You have your experimental units. You randomly assign them to 2 or more groups. They receive the treatments, and then you compare the results. Many students believe, a common error, that an experiment cannot be double-blind because someone has to know who gets which treatment. Although there's always someone who knows, okay, as long as the person doesn't interact with the subjects, the experiment can still be double-blind. The easiest way to describe random assignment is the same way that we could do random selection, which is using the hat method. Students often lose points because they make minor errors describing technology or the random table approach. Just make sure the slips of paper are the same size and they are well mixed, and you can always use your hat method. So we can use that hat method to randomly assign people to treatment groups. Last thing in the notes for today deals with what it means for statistical significance to occur. So in an experiment, researchers hope to see a difference in the responses so large that it is unlikely to have happened by chance variation alone. So what this means is we're looking for a difference in our results so large that we can make that conclusion that this happened because of this. Remember, I can only show cause and effect in an experiment. So we can use the laws of probability, which describe chance behavior, to learn whether the treatment effects are larger than we would expect to see only by chance. If they are large enough, we call the result statistically significant. So this is what's coming down the pipeline, but it's just kind of a preview. Say I find the average hours slept with 2 pillows is 8 hours, and the average hours slept with 1 pillow is 6 hours. Is that a large enough difference to prove that the number of pillows affects the number of hours that you sleep? That's where we're coming, okay? An observed effect so large that it would rarely occur is called, well, we're going to put by chance here, is called statistically significant. A statistically significant association in data from a well-designed experiment does imply causation. So if I have a well-designed experiment where I've used those principles of experimental design, and I have a result that's large enough that it could not have happened by chance, then I can prove causation or cause and effect. We'll answer what follows in the remaining parts in class. Good luck, guys, and see you then.